So good afternoon, dear friends, dear colleagues. Welcome to our optimization seminar. So it is my pleasure to introduce our speaker today, who is Michael Ulbrich from the Technical University of Munich. He received his PhD in 1996 from the same university and had shortly after that 2 research stays in the United States at Rice University. And yeah, very soon he became a professor of optimization at the University of Hamburg. This was in 2002. And 4 years after, he moved back to Munich, to his alma mater, where he's professor of optimization in the Department of Mathematics. And since 2008, he's also affiliated with the Department of Informatics. So Michael Ulbrich is working on many areas in optimization and optimal control. He's one of the experts in the area of optimization with the PDE constraints, doing theoretical investigations research, but also applied research. And I guess his topic today will be on his main areas of research. So optimization for PDEs, optimal control. So Michael, thank you for accepting our invitation. You have 45 minutes for a talk.
Thank you very much, Radu, for the nice introduction. It is a great pleasure to give a talk in this very nice One World Optimization seminar. Many thanks for the invitation and everyone for attending. I will talk on our recent work on an approximation scheme for distributionally robust nonlinear optimization. And towards the end of the talk, I will also discuss an application to PDE-Constrained optimization under uncertainty. But the main part of the talk will be in an NLP setting. This is joint work with Johannes Mills, and we received support by our international research training group, Munich and Graz. So we look at distributionally robust nonlinear optimization problems. I will abbreviate this DROP. And then we will make an approximation by using a quadratic expansion of the cost function and the constraints with respect to the random parameters. This will allow us to develop a tractable method in the sense that we can apply nonlinear programming software to compute first-order stationary points. This approximation by the quadratic expansion with respect to the uncertainty will lead to an approximated drop. And it turns out that then the resulting cost function and the constraint functions are sums of value functions of a semi-definite program and a trust region problem. And therefore, it is efficiently computable, these two value functions, but they are non-smooth. And since we are target at derivative-based methods, we then do a second step and construct smoothing functions for both value functions. And then we have a smooth approximated drop, and we use this to derive a continuation method to compute stationary points of the approximated drop. I will analyze the distributionally robust optimization problem, the approximated one, and the smoothed drop. For the continuation method, I will develop convergence results. And towards the end of the talk, I will discuss distributionally robust optimization with PDE constraints and show for this some numerical results. The problem we look at is of this form. So we have here a distributionally robust cost function and distributionally robust inequality constraints. Here the function f depends on our decision variable x. Most of the time x will live in Rn. And here we have a random vector xi. And the same structure is here in the constraints where we have functions gi. So let's discuss here the cost function. In stochastic optimization, one would take here the expectation, but in distributionally robust optimization, one does not assume that one knows exactly the distribution of the random vector xi. One just assumes that one knows an ambiguity set of probability distributions. Xi will, in our case, live in RP. And so therefore, distributionally robust optimization targets at robustifying against distributional uncertainty. Most of the talk will be in Rn, but when I move on to optimal control, then X will be a Hilbert space of controls. And in addition to these distributionally robust constraints, we also could have other deterministic constraints, for instance, expressed by a set Xat of admissible points. Okay, so this just repeats the previous slide. We are mainly motivated to tackle problems where F and G and the GIs are complicated. For instance, only implicitly given, not in closed form by a formula. And this arises, for instance, if we consider optimal control problems. There, X would be the control and F would be the reduced cost function. And to evaluate it, one would need the state of the system, and in the reduced approach, one would use the control to state mapping, which is implicitly given by a state equation. And therefore, evaluating F means solving a state equation and thus getting this implicit control to state mapping S. Some connections to other problem classes. As mentioned, in stochastic optimization, we would have this form. So we would assume that we know the distribution P of the random vector xi. And clearly, this can be viewed as a special case of distributionally robust optimization, namely if our ambiguity set just is a singleton containing the probability distribution, then the drop would reduce to the stochastic optimization problem. Then there's also the field of robust optimization, where one does not assume any knowledge about the distribution of the uncertainty, but rather one has an uncertainty set U in which one knows that the uncertainty will live. And then one robustifies by taking the worst case overall uncertainties in this uncertainty set. Now, also this can be viewed as a special case of distributionally robust optimization, namely if we collect in the ambiguity set that all DRX corresponding to the xis in the uncertainty set, then the drop would reduce to the robust optimization problem. In the following, to have a lighter notation, I first discuss the unconstrained case, because as soon as we know how to deal with this distributionally robust cost function, we can do the same with the constrained functions. Okay, so we just look at the unconstrained case for the moment. I will present a sampling-free approximation of this distributionally robust cost function, which for general F would be well, computationally intractable in general to evaluate. And so here we will do an approximation, and then I will develop a numerical strategy for this approximated drop that combines a smoothing approach and the continuation method, and that allows to use standard derivative-based NLP solvers. We have two papers on this. One appeared in SciOpt and handles the NLP case in finite dimensions, and one which is currently under revision, where we discuss distributionally robust optimization with PDE constraints. where this is an attempt to list some related literature. Of course, there's a vast amount of interesting literature in distributionally robust optimization and related fields. So here's important work on robust optimization. In blue are those approaches that are closer connected to our to what I will present than maybe the other references. And in distributionally robust optimization, there are different ways of representing the ambiguity set. Some work uses moment constraints, or other work uses distance to reference measures, for instance, using Wasserstein metric. And since at the end, I also discuss PDE-constrained optimization under uncertainty, I list here some work in this field. Many works on distributionally robust optimization use in a very sophisticated way optimization theory, and especially duality, to convert the maximization into a minimization. And for distributionally robust optimization, for instance, duality for the generalized problem of moments is important. And then one usually needs additional structure to come at the end to a problem that is computationally tractable. And there often the goal is to have a tractable problem in the sense that global solutions can be computed, for instance, in polynomial time. And in my case, tractability means that we can have at the end a problem where we can compute the cost function, the constraints and their derivatives, and can provide everything to apply an NLP solver. And this then is embedded into a continuation method. Our ambiguity set looks as follows. It is closely related to the one used in this paper by Delage and Ye. We consider here all probability measures P such that the mean satisfies this ellipsoidal trust region constraint, and that the covariance satisfies these semi-definite lower and upper bounds. And then we also have this entropic dominance constraint. So this, for depending on the application, this could be replaced by other conditions. It implies that all finite moments exist, and then it ensures well-postness of drops for quite general and nonlinear cost functions. If one looks at this, then it is pretty clear that this set is non-empty and that it contains normal distributions where the mean satisfies the trust region constraint and the covariance satisfies the semi-definite bound constraints. We can show that the ambiguity set is weak star closed and tight. Now I sketch here the steps we take in our approach. First of all, we assume that F is sufficiently smooth with respect to the uncertainty to use Taylor's expansion, or some, we also could use other expansion techniques to approximate F as a quadratic function with respect to the uncertainty. So what we need is that we are then quadratic with respect to the uncertainty. We do not need that we use Taylor's expansion. And well, our working hypothesis is that now if in the distributionally robust cost function, we replace F by this quadratic approximation in Xi, then this is sufficiently accurate for our purposes. This would, for instance, be satisfied if the ambiguity set is not too big. This step is needed to have a chance to get a tractable problem class. And now, therefore, now we have our approximated drop where we replace the f by this function that is quadratic in xi and nonlinear in x. And now it turns out that this distributionally robust cost function is the sum of two value functions, namely the value function of a semi-definite program and the value function of a trust region problem. I will show this in more detail. And then in the next step, since these value functions are in general non-smooth functions depending on x, we smooth it by constructing smoothing functions. This then gives us what I call smooth drop. And to this, we then can apply nonlinear programming solvers. And we embed this then into a continuation method, driving the smoothing parameters to 0. And then I will study convergence of the continuation sequence towards solutions of the approximated drop. Okay, so this repeats the last slide. I want to mention that the idea of using Taylor expansions appears in several other works on robust optimization and risk measure-based optimization. And I have listed here a couple of references where this is used. Well, now since we have a quadratic dependence now of our approximation Q on xi, it is not difficult to show that then this value function, so this distributionally robust function, is the sum of two value functions, one of this semi-definite program with a special structure, and one of this general trust region problem. So we do not assume convexity here, it can be non-convex. And well, as we know, for this SDP, we can we can solve the SDP efficiently up to high accuracy. And it's also possible to solve the trust region problem to high accuracy and to global optimality. But of course, then these value functions depend in general in a non-smooth way from x. So we can compute them, but now if we want to work with this, we need to work with non-smooth optimization methods. So we go a step further and develop smoothing functions for these two functions. And this then will lead us to a continuation method. I explain it here. So this is the problem we want to solve. We construct smoothing functions for the SDP value function and the trust region value function. In a natural way, we will have three smoothing parameters. We collect them in this smoothing parameter vector rho. If we fix the rho, then these smoothing functions are, well, as smooth as we wish with respect to x, and we can solve this by a nonlinear optimization solver to a desired accuracy. We will work with a sequence of approximately stationary points. And well, if we are in a later iteration, then of course we use here as an initial point the solution from the previous iteration, and then we drive the smoothing parameter to 0. And well, we use smoothing functions in the sense of Chen and colleagues and the underlying theory. Of course, later we can do the same for our distributionally robust constraints to also handle constraints in a similar way. And I will show convergence results for this approach. Before I start introducing the smoothing functions, I want to repeat the general concept of smoothing functions. So we are given a continuous function phi, and a smoothing function phi tilde for this phi is a function that also now depends on a positive vector rho, the smoothing parameter, and is continuously differentiable with respect to the original variable x. And we need this uniform approximation property of the smoothing function. And this gamma is a forcing function that tends to 0 if rho tends to 0. And then there's also the concept of gradient consistency. Here, this is Clark's differential of the function phi. And this S phi tilde is the convex hull of limits of gradients of the smoothing function corresponding to sequences xk rho k converging to the point x and the smoothing parameter 0. And gradient consistency holds if we have this equality. Okay, now we construct smoothing functions in this sense for the SDP problem. Since this is not an SDP in its general form, but we have the structure of these bound constraints in an SDP sense, it turns out that one can compute the value of this based on the eigendecomposition of this matrix here. This is a symmetric matrix. And this turns out to be more efficient than applying a general purpose SDP solver here. And so the main work in computing this function or evaluating it at the point x is to compute the eigenvalues of this symmetric matrix. Now, of course, we still have here non-smoothness because of the max and the eigenvalues. We use an entropy function of this form to smooth the max. This function then is analytic, and then if we replace the max by this analytic smoothed version, then by the theory of spectral functions, this becomes smooth if the underlying problem functions are smooth. And we can prove that by this we get a gradient consistent smoothing function, and we can prove these estimates. So the error we make with the smoothing function is proportional to the smoothing parameter. And well, using theory of derivatives of spectral functions, it turns out that also computing the derivative of this smoothing function is efficiently possible if you have an eigendecomposition of this matrix B. Okay, and now I move on to the trust region problem. We had an ellipsoidal trust region constraint, but to make the considerations here simpler, I moved to an Euclidean ball, and later by a transformation of variables, we can apply this then to our more general trust region problem. So here we have a general, possibly non-convex quadratic cost function, trust region constraint, and we want to construct a smoothing function. And the smoothing function we will end up with is again the value function of a trust region problem in 2 dimensions higher than the original one. And the underlying matrix and gradient here have this form. Here are our original data H and G, and here we have 2 additional diagonal entries, and here we have small perturbations with a smoothing parameter. And this E is a smoothed version of the maximum eigenvalue of the matrix H. Like before, one can show that this then is an analytic spectral function independence of H. And if one looks closer, then this modification avoids the hard case, and then one can already guess that the value function of this is smooth. But actually our derivation was different, and I show this on the next slide. So our idea was to use duality. So there's a nice duality theory for trust region problems. For instance, can be found in this paper by Stern and Henry Wolkowitz. And now the dual problem can be written in this form. The dual function is down here. We have here a strict inequality. So otherwise we would have to write the pseudo inverse here. Now there are whole strong duality, so we have equality here. Now there would be several ways to proceed, but to arrive at the end at the trust region problem again, we do the following. First of all, we replace we approximate this lambda max by a smooth version. This was introduced on the previous slide. And then to remove the dependence on age in the constraint, we approximate this by the optimal value of a barrier formulation of this. And now to do the barrier approach here, there would, of course, one could use the log barrier. This would be possible. One also could use a log det barrier based on already on this version, but we use here a reciprocal barrier because then one can observe that this is the dual problem of a trust region problem. So there would be several ways to do it, but with the reciprocal barrier, we can again take the dual and then arrive at the previously shown trust region problem. Okay, and here the difference now between this one and this one is that this function now is smooth because the hard case is avoided, and the smoothness can also be shown by strict convexity of this barrier function. Okay, so the resulting lifted trust region problem has a unique optimal solution, and sensitivity analysis and Dunskin's theorem shows that the corresponding value function is as smooth as the function G and the matrix function H depend on X. Again, we have a uniform error estimate. And from this follows that we have indeed a smoothing function, and we also can prove that gradient consistency hold. So by now we have constructed a smoothing function for the SDP value function and for the trust region value function. In our computations, we observe that if we apply the Morey-Sorensen algorithm to solving this trust region problem, we usually need about 5 iterations or so. So we can evaluate this value function quite efficiently. And also computing the derivative of this smoothed value function is quite inexpensive by Dunskin's theory. Okay, now, as I said, we look now at the trust region problem with an Euclidean ball, but originally we had this ellipsoidal trust region, but clearly if we do this change of variables, then we can bring this to the Euclidean ball, and well, then we have to introduce this H and this G, and with these substitutions, the value function of the Euclidean ball trust region problem gives us the value of this trust region problem. And the same holds true for the smoothed version, so for the lifted trust region problem. Okay, so therefore we now have smoothing functions for both parts. So I collect what we did so far. We had this problem here, this distributionally robust optimization problem. To make it tractable from an NLP perspective, we replaced the F by a quadratic expansions in terms of psi. This, of course, would be exact if we would have a quadratic dependence of f on psi. Otherwise, we have an approximation here. Then we have this approximated drop. We observe that this here is the sum of two value functions. And then we derived smoothing functions for these two add-ins. And now if the dependence of f and the psi gradient of f and the Hessian with respect to psi of f depends in a CQ manner on x, then the cost function of this smoothed drop is also CQ. So we can have this as smooth as we want if f is sufficiently smooth. We thus can apply standard optimization solvers. Okay, now we extend this to distributionally robust constraints. Maybe you guess already how we do this. We just deal with this supremum over the expectations exactly as we did for this one. So we approximate the GI by a quadratic expansion with respect to xi. Then we arrive at this approximated drop, where we have the quadratic functions in xi here in the expectations. Then again, here we observe that for this quadratic function, the expectation is again the value function of an SDP and the trust region problem. We can construct smoothing functions as before, and then we can arrive at the smooth approximated drop, where we use the smoothing functions in cost function and constraints. And this then is a standard NLP for which we can compute stationary points using NLP solvers. Okay, now concerning convergence, let me introduce some abbreviations. For the approximated drop, I call the cost function capital F and the constraint functions capital GI. These are non-smooth functions, and the smoothing functions for them are capital F tilde and capital GI tilde. Now, the approximated drop can be written as this non-smooth constraint optimization problem, and we can write down KKT type conditions by using Clark calculus in this form. And the smooth approximated drop has smooth functions, so we can use the KKT conditions. And in our continuation method, we will work with epsilon k KKT pairs. This means we compute tuples xk and lambda k that are KKT pairs up to a tolerance epsilon k of the smooth drop. Okay, we can show that if the approximated drop has a strictly feasible point, then if the smoothing parameter and the smoothing vector is sufficiently close to 0, then also the smoothed approximated drop is feasible. This is just a continuity argument. Further, we can show that if we compute epsilon k stationary points for a smoothing sequence rho k converging to 0, and the corresponding KKT or epsilon k KKT triples are xk lambda k, then any accumulation point of this sequence is a KKT pair of the non-smooth approximated drop. As we will see later for the PDE-constrained case, we also could work with global solutions of the smooth drop and then show convergence to global solutions of the approximated drop. Okay, so now this almost concludes my part on the NLP drop problem. We have numerical results for this, but since I also have numerical results for the optimal control problem, I will skip the other numerical results here. Just a few words on this. We constructed drops by using an unconstrained test set by Moray-Gardov-Hillstrom. And we made the problems, so we introduced uncertainty in this additive manner. And then we compared three approaches. Our continuation method, where we use the BFGS method, globalized BFGS method. Then a state-of-the-art non-convex bundle method by Mekele and colleagues directly applied to the approximated drop. And one also can write the approximated drop as a nonlinear semi-definite program. And so the third comparison was with a two-pen lab applied to this nonlinear SDP. And so we observed that our method is competitive and that it needs the lowest number of higher order derivatives than the two competitors. But these methods also worked quite well. A main advantage of our approach is that any NLP solver can be used and that it is quite easy to handle even complex and distributionally robust constraints with our approach. Okay, you will see numerical results then for the optimal control problem. And now I move on to distributionally robust optimization with PDEs. I change notation a bit because, well, calling X the control would be pretty non-standard. So I now use U for the control. We have an admissible set U at, so U plays the role of X now. The rest is the same as before, but F now is J hat, because J usually is used for in optimal control for the cost function. And this is the reduced cost function. Well, the rest is similar as before, just J hat replaces F. And we are now in a Hilbert space, which is usually infinite dimensional in our context. Now, I showed this structure before. J hat is the reduced cost function. To evaluate it, one needs the state corresponding to the control and the random parameter value, and then plug this into the state-dependent cost function to get the reduced cost function. And S is the solution operator of this state equation, which for the moment I write in abstract form. So it's usually a nonlinear equation with a unique solution y given u and xi. And this then induces the solution operator S. And we are here, this equation is posed in a Banach space setting. Okay, now some assumptions in order to start the existence of solutions of the drop. We assume that the PDE has a uniquely defined solution operator capital S. We need that this solution operator is weakly continuous as a function of the control, and it is continuous as a function of the random parameter. From the cost function, we have the following. For the cost function, we have the following requirements. It is continuous in all variables. With respect to state and control, it is weakly lower semi-continuous. And now the next two properties could be expressed in terms of J, but it is more convenient to write it in terms of the reduced cost function. We need a uniform lower bound to ensure existence of solutions. And we need that if we fix U, then the reduced cost function is a random variable uniformly integrable with respect to our ambiguity set. And this means that this condition is satisfied. This is needed to show weak lower semi-continuity of our distributionally robust cost function. And finally, to get some boundedness of a minimizing sequence, we need this boundedness of a sublevel set. One can find similar assumptions in other contexts, for instance, in Curie and Sorobiek. And okay, this just repeats the assumptions you saw on the previous slides. And based on these assumptions, we can prove the following theorem. First of all, the distributionally robust cost function for the optimal control problem is finite valued and weakly lower semi-continuous. Now, if U at is closed and convex, or more generally weakly closed, then the drop has an optimal solution. And we also can show that if we fix the control, then, so this is the distributionally robust cost function, there exists a worst case distribution. So this sub is actually attained by a distribution in the ambiguity set. Okay, now this was existence of the solutions of the original drop. And now we develop similar results for the approximated and the smoothed drop. maybe I do not have to go through all the assumptions. So under reasonable assumptions that are verifiable for the application I will show you later, we can prove that the distributionally robust cost function of the approximated drop and its smoothed version is weakly lower semi-continuous. Therefore, the approximated drop and the smoothed approximated drop have optimal solutions. And now if we look at a sequence of solutions UK to the smoothed problems for rho k tending to 0, rho k is the smoothing parameter, then we can show that this sequence of controls is bounded and therefore it has weak accumulation points, and we can show that every weak accumulation point solves the approximated drop. So we have a convergence result for our continuation method. Okay, now concerning, so we need several derivatives to make our approach work, because we had this Taylor expansion with respect to psi, and then we want to apply a derivative-based method. So we have one additional differentiation with respect to the control. So we use Phoenix for discretization. And for Phoenix, there's a nice package Dolphin adjoint, which computes gradients in an adjoint-based way. But we need higher order derivatives, and Johannes Mills now extended this approach to higher order derivatives. And we have formulas for all required derivatives, but they also can be found in work on robust optimization by Stefan Ulbrich and colleagues. We combine, to compute the derivatives efficiently, we combine sensitivity and adjoint approaches. In our numerics so far, the random parameter has not too high dimension, then it is most efficient to compute the full Hessian with respect to the random parameter. And well, then if we do this, then, and we count how many PDE solves we need to compute the approximated drop cost function and the smoothed approximated drop cost function, we get that we need one state solve and P linearized state solves and P plus one adjoint solves to obtain the function value. The same for the smoothed function value. And if we want to have the gradient of the smoothed function value, we have P additional linearized state solves and P adjoint state solves. If P is not too big, and there are many applications where the number of uncertainties is not too high, then this compares very favorably to sampling-based approaches, where typically one needs tens of thousands of samples to approximate expectations. Okay, now I move on to a concrete problem, namely optimal control of the steady Burgers equation. Here, this is the state equation for this example. It is nonlinear. It's structurally similar to Navier-Stokes equations, but it's a 1D equation. So here in blue, you see where uncertainties enter on the right-hand side in the coefficient and in the boundary conditions. And well, here you see some of the random parameters appear in a quite nonlinear way. This problem is inspired by this paper here. Okay, and now we can show that all our abstract requirements are satisfied for this problem class. So uniform integrability, sufficient smoothness of the solution operator. Here in the stationary case, we need that the viscosity parameter is sufficiently big to have a unique solution. And well, using implicit function theorem, we can show that the control to state mapping is sufficiently smooth, and we can verify all assumptions of the theory I showed you. Now, to discretize, we use continuous piecewise linear finite elements. And in our continuation method, we start with this smoothing parameter triple. And then after each iteration, we damp it by 0.1. We use an LBFGS method in the Muller package. Our termination criterion of the outer loop is such that we do 3 outer iterations. This turns out to be sufficiently accurate. And our trust region subproblems are solved by the Moret-Sorensen algorithm, and it requires just 5 iterations or so. Now, here you see some pictures about the computed optimal controls. So here, delta parameterizes the size of our ambiguity set. And in orange here in the pictures, so on the left, you see the optimal control. In orange, this is the control that you get if you solve the nominal problem, where, so to say, the center of the trust region for the mean is used instead of psi. And here you see several solutions. For different sizes of the ambiguity set, you see quite some difference in how the optimal control looks like. So the robustness matters in the type of the control, and you see the larger the ambiguity set, the bigger is the difference. So the black one is the control for the largest ambiguity set. And here you see corresponding controls evaluated for psi equal to mu bar. State, these are the states, and the states would be random fields, so we have to evaluate it for a specific psi value. Here you see some numbers on iterations. So this is the outer loop. Here you see a number of iterations of the LBFGS method that we need. Here, number of smoothing functions, evaluations, and gradient of the smoothing functions, so all quite moderate. And here you see the relative change, well, of the computed control from outer loop to outer loop. So this goes to 0 here. And well, now, so this means we can solve the approximated drop quite efficiently with our approach. But since this is only an approximation, we also studied how well it robustifies the original drop without the quadratic approximation. And well, we cannot solve the original problem is too difficult, so we only can, it cannot be solved to high accuracy. So we did the following. We draw PIs randomly from our ambiguity set, and then this can be viewed as a Monte Carlo approximation of our distributionally robust cost function. And these in the same way use other, instead of the expectation here, the standard deviation and the value at risk. So these can be all viewed as robustness measures. And you see for all robustness measures, the distributionally robust solution performs better than the nominal solution. So our approximated drop gives for the original drop more robust solutions than the nominal one. This is an indication that the approximation does not deteriorate the robust solution much. Well, and how is the time? So, because I have now similar results for the time-dependent problem.
Yeah, 2 more minutes, Michael.
Okay, good. So this is fine. So here we have the Burger's equation, but time-dependent. So this is a more complex then. We have again, now we control the Neumann boundary condition on both sides. Previously, we controlled the right-hand side. We have again in the coefficient uncertainties right-hand side initial condition. Again, we can verify our theory step by step, studying the state equation and the properties of the solution operator. And so our theory is applicable. Now we discretize in time by implicit Euler and in space by linear finite elements. We have a similar continuation method as before. We start with the solution of the nominal problem. And again, we use limited memory BFGS. And here you now see we had on the left-hand side, we had the control, and on the right Neumann boundary, we had the control. Here again, orange would be the nominal optimal control without robustification. And here in black, you see for the largest ambiguity set the optimal control. Again, you see quite a difference in how the optimal control looks like. We have, well, similar numbers of iterations and function evaluations again for this problem. And again, if we look at our quality measures of robustness for the original not quadratically approximated drop, we again see that the distributionally robust solution of the approximated drop is much more robust than the nominal solution is. So we get a robustification of the original problem. Okay, then I come to the conclusions. I developed an approximation scheme for distributionally robust optimization, where we replaced the original dependence on the uncertainty by a quadratic one that can be non-convex. We do this in the cost function and in the constraints. We designed a continuation method based on smoothing of the resulting value functions and proved convergence of the continuation method. And then at the end, I moved on to PDE-Constrained distributionally robust optimization, where we then studied also the applicability and existence of the solutions, and I showed you some numerical results. So thank you very much.
Thank you very much for a very clear and very interesting talk. Are there questions? Henry.
Yes. Yes, I was wondering, so one question was about the trust region application, and you mentioned that you proved that the hard case never appears. So one of the things about the hard case, I think, is that generically the hard case doesn't occur. But can you say anything about, does it happen that you have the near hard case, which makes the problem hard? You understand what I mean?
We could have the hard case here. So in the original trust region problem, but our approximated drop, for which we then can estimate the difference between the true optimal value of the trust region problem and the one of the approximated one, there we can prove that the hard case does not occur and that we have a smooth dependence of the solutions on the parameters. And if one looks here, so one can see it. So, well, we always need that the lambda is greater or equal than 0. And so here we have a maximization problem. So the lambda has also must be greater or equal than lambda max of h. Yeah, in the trust region optimality conditions. And by this here, this is an upper estimate, an upper approximation of lambda max. And so this will give us so we have here eigenvalues here. So this will contribute to the eigenspace of eigenvalue 0. And this will be bigger than lambda max of this here. And because we have non-zero entries here, one sees that the true hard case can never occur for this specific trust region problem. So this is the reason why for this specific version of the trust region problem, we do not have the hard case. Of course, if the parameter becomes small, but this is typical if we have a smoothing method, if we drive the smoothing parameter to 0, then we approach the original problem and then we can get close to, I would say we can get close to the hard case. Does this give a satisfactory answer?
Sort of answers the question. I don't know if you actually do get the hard case, if you can actually exploit the structure if you do know that you have the hard case. And the hard case becomes the easy case. I mean, the hard case becomes easier than the easy case.
Yes, but still so we have a parametric trust region problem because we are interested in the dependence on X, and this enters via the matrix and this G. And even if it would be easy to handle the hard case from the trust region perspective, still the value function can be non-smooth in the parameter. And this is what bothers us. So we want to have smoothness with respect to the parameter. It is not that we can efficiently solve the hard case for the trust region problem. I know that there are ways to do this. We want to avoid possible non-smoothness of the optimal value with respect to the parameter X, which enters via the matrix and the vector.
Okay, and what was the size of the problems you used Morey-Sorensen on?
So currently this was also for our NLP test problems, this was never beyond the hundreds. So there would be a point where it would be good to go, for instance, from Morey-Sorensen method to iterative solvers for the trust region method. I also had one bullet point on one of the slides. So if P becomes very large, then it would pay off to go to iterative methods. And also for the SDP, there we needed the eigenvalues. There one then could use iterative methods to compute the eigenvalues.
Okay, well, thank you very much.
Thank you.
Thank you. Are there other questions? So I have a question, Michael. So, so my impression is that this smoothing approach is very flexible.
Yes.
So what would be other, let's say, smoothing functions which would work in for your problem, or I mean, or are these the only ones?
No, there would be options. Well, so for instance, let's look at the trust region problem. Here you would have the option to write this as a semi-definite constraint. And then, for instance, well, using this, so our idea was, okay, we said we have a non-convex problem. If we want to get this smooth, then somehow we need something that has maybe a unique solution. Then the idea was go to the dual, then it's already convex. And then if we make it strictly convex, we have a chance that we get smoothness with respect to parameters. And well, so this is why we then at some point use here the barrier approach. There might be other ways. So we want to get the parameter dependence out of the constraints because this limits smoothness. It's better to have this in the cost function, smoothness wise. And So either one has a specific structure such that dependence on a parameter in the constraints does not spoil smoothness, or well, instead of a barrier approach, one could have a penalization or maybe an augmented Lagrangian approximation. Also, if you stick to barrier, we could use here log barriers instead of reciprocal barrier. Then still you can do something like Morey-Sorensen algorithm, which essentially solves the dual problem. You just would have a different structure, but you could do this also for the log barrier terms here. It was just, I found it a nice observation that Johannes Mill said that if we do this, then we can return to the primal setting and have a trust region problem again. The other way would be if you do a log barrier here, well, you could write this as a semi-definite constraint and then use the log det barrier for the semi-definite constraint. Then you could go directly from here to here with log barriers without smoothing this lambda max, because the lambda max would no longer appear. And I think any reasonable way to get a smooth approximation of this cost function of this problem would lend to a reasonable choice of a smoothing function.
Okay, but then it's not clear which is the best choice from a numerical point of view, or
yes, this would be, and so far, so we did not do experiments on several possible choices. We were happy that this approach works quite nicely, and since we applied it in an optimal control setting, well, this is always a bit involved to get this implemented.
Okay, thank you. Then I have a second question. So in the smoothness approach, there was a second condition which is relating the subgradients of the non-smooth function with the limit of gradient of the smooth function.
Yes.
So is this condition relevant at some point in the proof?
Yes, we need it for the result where we consider stationary points, so KKT or epsilon K KKT pairs of our smooth problem. And then we prove that if we drive the smoothing parameter to 0 and look at accumulation points, that this satisfies the KKT conditions in a Clark sense. And there you need this. Otherwise, for instance, if you look at, say, global solutions and prove convergence to global solutions of the unsmooth problem, then you do not need this.
Yes.
And actually, it is not so straightforward to extend the gradient consistency condition to infinite dimensions, because already the Clark-Jacobian is originally defined with strong limits of Jacobians, and well, there are extensions by Thibault and others to infinite dimensions, but it's a bit involved then.
I agree. Thank you. So if there are no other questions, I propose to stop here and to thank Michel again for a very nice talk and a very nice discussion.
I have a question.
Oh, we have questions. Okay.
Yeah. So what was your motivation behind your presentation?
The motivation was, so I did in the last years, I did quite some work on PDE-Constrained optimization under uncertainty. And very often you then end up with having expectations in high dimensional spaces where, well, evaluations are expensive because every sample would require to solve a PDE to just evaluate one instance of the cost function. So the idea was, can we find a reasonable robustification without having to approximate expectations by sampling? And so this was the original motivation.
Okay.
And as I said, if this dimension p of the random vector is not too high dimensional, so if it does not go beyond, say, 1000 or so, then complexity compares quite favorably to Monte Carlo approaches.
Okay. Thank you.
Thank you. Are there other questions? So everybody's happy. Thank you very much, Michael, for the nice talk. So we
Thank you. I would like to thank everyone who attended.
Thank you. I just want to say that we will post the video and the slides on the website of our seminar, and to announce that our next speaker will be Arsen Donchev next Monday, same time. Thank you very much. Yes, I wish you a nice week. All the best. See you next Monday. Thank you, Michael.
Have a nice week. Thank you.
Another question. Can you get a slide?
Yes, it's what I said. We will post them on the website of the seminar.
Okay, thank you.
Yep. Okay. Okay, thank you. So then Michael, I just want to ask you to send me the slides.
Yes.
At some point today. Okay.
Okay.
Thank you.
Bye-bye.
Bye-bye. Thank you. Bye-bye.